My name is Stephen Bates, and today I'll be talking to you about the Pythagorean Theorem and its converse. So, the brief history: Pythagoras was born in 580 BC, and as a child he was interested in mathematics, philosophy, astronomy, and physics. He created the school of Pythagoras in Crotona, where they studied philosophy and religion. His followers were known as Pythagoreans. They studied numbers in the abstract, and they related music to math. The Pythagorean Theorem in Euclidean geometry defines a relationship between the legs and the hypotenuse of a right triangle based on the properties of a square. So basically you cut a square in half on its diagonal and then you use a triangle. To start his proof, Euclid constructed a square of area a plus b quantity squared, which with rectangles GBIF, EDIH, and square CHIF inscribed in ABCD. He proclaimed that the area of AGIE was a squared, that the area of EDIH was AB, the area of GBIF was also AB, and that the area of CHIF was b squared. Hence, the EDIH is equal to GBIF. The area of square ABCD is equal to the sum of the areas of the individual quadrilaterals within. Thus, the area of ABCD equals a squared plus b squared plus 2ab, which is equal to a plus b quantity squared. To continue his proof, Euclid then took another square, JKLM, equal in area to ABCD, which is a plus b quantity squared, and inscribed a square with side length c within it. Right triangles were formed with sides a, b, and c. All of the right triangles had area a times b over 2, and the area of the inner square was c squared. Hence, the total area of square JKLM is the sum of the areas of the inscribed shapes. So, c squared plus 4 times 1/2 AB, because there are 4 triangles, and we get the area of JKLM is c squared plus 2AB. To finish his proof, Euclid realized that the two squares ABCD and JKLM had the same area, a plus b quantity squared, and therefore those squares are congruent. Thus, the sum of the inscribed shapes were also equal. So now we have a plus b quantity squared equal to c squared plus 2ab. Expanding a plus b quantity squared out, you get a squared plus 2ab plus b squared equals c squared plus 2ab. Cancel out the like terms, and you get a squared plus b squared equals c squared, which we know to be the Pythagorean theorem. Now, when the Pythagorean theorem is taught, the converse is also taught. Euclid's Elements, the previous proof was followed by a proof of the converse, which stated, if in a triangle ABC the square on one of the sides, say BC, is equal to the sum of the squares on the other two sides, then the angle contained by these other two sides is a right angle, or an angle whose measure is 90 degrees. So, to start his proof, Euclid made the following model: the triangle BCD with altitude AC down the middle, and AD perpendicular to AC, and AC is equal in length to AB. By hypothesis, AC squared plus AB squared equals BC squared, and the Pythagorean theorem, when applied to the triangle CAD, implies that side AD squared plus side AC squared equals side CD squared. Because AD equals AB by the definition of a bisector, the implication is that BC squared equals CD squared, thus making BC equals CD. Since CA is perpendicular to DB, angle DAC and angle CAB are right angles. Thus, triangle CAD and CAB are congruent by SAS congruency, and then by CPCTC, measure of angle CAB equals measure of CAD, a right angle. To show that the Pythagorean theorem holds while looking at the Euclidean form of the parallel postulate, I'm going to examine the 3-4-5 right triangle. The 3-4-5 right triangle is a special right triangle because it adheres to the rules for a Pythagorean triple. So pretty much the lengths of the sides are going to be 3 and 4 for the legs, and then the sum of the squares of those will equal the hypotenuse, which will be 5. So let's just make this diagram here. We'll do a 3, 4, and connect dots. So let's just make sure that the angle B is 90 degrees. So we get an accurate reading. The angle around angle B is 270, which we can conclude angle B is 90. So let's find the lengths of the sides. We see that side AB is length 3, and that side BC is 4. This should lead us to presume that line AC will be 5, but let's just take a look. So we know from high school geometry that the Pythagorean Theorem is defined as a squared plus b squared equals c squared, where a and b are the legs and c is the hypotenuse. And then we can solve for c by taking the square root of both sides. So c equals the square root of a squared plus b squared. Now we know that a in this case is 3 and that b in this case is 4. So now to solve for c, we're just going to substitute in a and b. So c equals the square root of a squared plus b squared. We get c equals 5, which is what we expected. Now we'll just go here and make sure that that's true, and we see that the side length equals 5.